Shotcrete is divided into two distinctive categories, dry mix and wet mix. The dry mix process does not use water until the shotcrete is applied outside. The wet mix process uses water during mixing as you would for conventional concrete. An example of wet and dry mix shotcrete compositions is displayed in the table. Shotcrete consists of cementitious material such as Portland or blended cement and silica fume in ratios of 5 to 15% by weight. Fine aggregates less than 5 mm consist of gravel and sands, which make up the majority of both mass and volume. Admixtures are chemical additives which alter mechanical and physical properties. Water is ideally of drinking quality, free of dissolved solids with a pH greater than 5. Other sources can be used if necessary. Admixtures include water reducers to create a fluid concrete without adding more water, air entraining agents to produce minute bubbles within the shotcrete, accelerators to speed up the hydration reaction, and retardants to slow down the hydration reaction. Shotcrete is weak in tension, so fibres are combined to improve the tensile and flexural strength. Steel fibres are most commonly used due to their high performance. Synthetic fibres are used less often and mostly for controlling shrinkage cracking. Glass fibres are used minimally for lightweight panel construction.
The manufacturing of shotcrete is similar to that of concrete, however there are some distinct differences to note. There are two types of shotcrete manufacturing plants. A ready-mix plant that combines the components and a cement truck is required to mix it in transit, or a central mix plant that measures and mixes the shotcrete at the same location. Dry mix shotcrete can be manufactured at factories, coming to site in pre-made bags, or as raw ingredients can be combined at a shotcrete plant. Wet mix must be manufactured at shotcrete plants to have a close proximity to the application site to avoid the hardening of the shotcrete. Application will also vary between the different types of shotcrete, as dry mix will utilise compressed air to move the mixture through the hose to the nozzle where the water will be applied. However, wet mix is moved through the hose through the use of mechanical and hydraulic power, where air is added along with the required admixtures at the nozzle.
The strengths of Shotcrete include tensile strength, electric modulus, shear strength, and so on. Tensile strength is a measure of the force a material can absorb through plastic and elastic deformation until necking begins to occur and the material falls. The elastic modulus is the uniaxial stress state divided by the strain in a direction. The elastic modulus of Shotcrete varies dramatically due to different projection process. The deformation of Shotcrete include hot shrinkage, dry shrinkage, crepe deformation. The range of dry shrinkage is determined by the water contact of the Shotcrete. If the potential of the water is high, the shrinkage range is relatively large. The hot shrinkage is caused by the thermal output during cement hydrogen process. This shrinkage is further with a quick setting agent.
The slump test indicates the mixed consistency of wet concrete. Shotcrete would typically have a large slump reading as high workability is needed to reduce pump pressure. Furthermore, compressive strength testing is conducted on core samples taken from a test panel that is made on the same day of application. Cores are tested after 28 days to truly reflect a shotcrete wall's strength, which is in accordance with the Australian Standards 1012.14. Early age strength is vital for shotcrete as it needs fast structural integrity. This is to ensure it stays in its sprayed condition on the wall. Flexural strength testing measures the bending capacity of shotcrete. This is improved by fibre reinforcement, which is linked to the toughness of shotcrete.
The spray-on properties of shotcrete is one of its characteristics that makes it so advantageous compared to other conventional methods. Some applications where shotcrete is exemplified can be seen where there is impracticalities in accessing work sites, achieving variable layering thickness specifications in engineering design, or where normal conventional methods of casting are unemployable. Shotcrete can be used to revitalise the deterioration of walls and roofs after earthquakes, as well as repair to beams, columns and other members responsible for building stability. It is often encased around structural steel members to improve fireproofing properties. Shotcrete can prevent any further degradation of the slope and assist in preventing any minor falls in the future. Most tunnels need some form of ground support. It is increasingly becoming legislation, especially in the mining industry, to provide full ground support in all tunnels in construction and post-construction. As a result, the characteristics of shotcrete is becoming increasingly popular due to its advancements in efficiency of installation. Shotcreting and drilling occurred on the spillway upgrade of Jindabyne Dam in 2007. Mesh reinforced shotcrete was employed and used locally to maintain a tight rock face within areas of jointing.